Hey guys, Professor Hughes here. Informal video again on the cycloid. The cycloid, very interesting geometric figure. It has all kinds of uses in engineering, and my little thing here today is to go ahead and get a formula for the tangent. I couldn't find anything out on the internet, believe it or not. It's probably there, but I couldn't find it. Something quick, simple. And that will also help you with the Brachistochrone problem. So you can look that up, find out what that's all about. The tangent will tell me at any instantaneous point on that curve the velocity the thing is going and in which direction it's going. So again, a lot of really cool applications. It's just phenomenal stuff. So this is a rather high level math formula derivation here, guys. You're going to need a fair amount of trig, and you're definitely going to need to know algebra. Alrighty, I don't go through like total step-by-steps, but I give enough indication where if you wanted to kind of grab it and work it out on your own, it's kind of fun, actually. I mean, I had a good time doing it. It took me, I think, about half an hour, and I thought I wanted to start with the Law of Cosines. And this is what I came up with that. Okay, that's not a really pretty formula to use, okay? I decided to use the Law of Cosines. Though a little heavier up front, wait till you see what happens in the rear, okay? And a little trick for you at the end of the video. I'm going to come back and share that with you. All right, go ahead and enjoy this. This is fun stuff. I love it. This is a cycloid, alrighty? The y-axis, or the distance, is really the diameter of the rolling circle, or what we call the generating circle. The time arrow is actually the x-axis, and this is a geometric way to go ahead and form the cycloid, alrighty? And we're interested in the actual tangent at anywhere along this curve that we want. So let's go ahead and move on. This is the cycloid without all the accoutrement, if you will. And let's go ahead and put a point somewhere along the curve where we would like to find the tangent. We'll label it P. P for point. Sounds good. And we'll go ahead and cut the tangent right through that point along the curve. And in order to find the angle of that curve, we're going to go ahead and draw it to the horizontal, parallel to the x-axis, and that will give us an angle alpha. The next step is to draw a perpendicular through the tangent, making a 90-degree right angle with each side in order to intersect that line, that T line, okay? Because we really want to know the point T. That's really the crux. Whenever we have our formula at that tangent, you're going to go ahead and find the T value. Let's call that line H for hypotenuse. Let's go ahead and set up the y-axis so that we can cut the center line through the cycloid. This would be the radius. Remember, the diameter is from the midpoint of the cycloid to the base, and that midpoint right there is the 2 radii. So let's go ahead and draw a perpendicular line straight up to the radius, and we'll call that R. And from geometry, you know that the alpha at the tangent and the horizontal there is also equal to the alpha here at the point where T, H, and R meet. Let's go ahead and draw another radius from that center point up to point P, and what would we essentially will generate the exact same angle. Again, this is all geometric stuff. Now, we know that the triangle itself has 180 degrees, okay? Well, we're dealing with radians, so that's pi, and all I have to do is take pi and subtract the two angles and I have that third angle that's across from the hypotenuse. And here's where I wanted to go into the law of sines. Again, that got really big and ugly. So all of that said and done, I decided that I'd go ahead and use the law of cosines. So let's go ahead and, from point P, let's go ahead and draw a line straight down to a point X on the baseline, all right? And let's go ahead and cut our Y so that we understand exactly where that point is on the Cartesian plane. Let me move X and T down here, give a little bit of space so that we can include the side A, which I will need. That's the distance from point X to point T. And then the parametric equation for X is T minus the sine of T. And one last thing we're going to do, I can't extend it toward the left, so let's extend it toward the right. I'm going to go ahead and include the parametric equation for our Y. Now I have all three sides of my triangle prepared. I have my leg at X, I have my hypotenuse, and I have my leg at A. Here's what we need to do to finish off the derivation. I need to find A. I need to find H using the law of cosines. So I'm going to go ahead and use Pythagoras' theory. Yeah, it's the Pythagorean theorem, but I had a great math teacher who, in high school, you're just kind of not ready for stuff and you don't really care much. But his name was Mr. Vian. Great guy. Super good teacher. I just wasn't ready, And he used to call it Pythagoras' theory. So always remembered that. He always seemed like he had his necktie too tight. God rest his soul if he isn't around today, but that was some years back, right? So finally, after all this, we can then solve for T. So our first step was to find A. Well, that seems easy enough. If you'll notice A, and I have the diagram kind of in the background for you so that you can see it at any given time, which I thought was, kind of fun. So A occupies the space between X and T. Well, then I just take T and subtract the parametric equation, and I should come up with A. So let's go ahead and solve that real quick. We get rid of parentheses, and there's our A. It's sine T. How fun. That's actually pretty easy. All right, the next one's a little funner. Here's where I use the law of cosines. Law of cosines, in different books, it's different things, but I always remember C squared equals A squared plus B squared minus 2AB times the cosine of that opposite angle, which in this case, if I'm using C, it would be gamma. I think that is the way the Greeks pronounce it, baby, gamma. Okay, so here it is. I have H squared. We use radius squared plus radius squared minus 2 radius squared times the cosine of the quantity of that angle, which is pi minus 2 alpha. Of course, the radii are all 1, and that makes life real easy for us. We wind up with 1 plus 1. You can read the rest there. And the bottom line is I come up with h squared equaling 2 minus 2 cosine times the quantity of pi minus 2 alpha. And we square root both sides, and that is our beautiful h. The square root of 2 minus 2 cosine times the quantity pi minus 2 alpha. Oh, what a gorgeous formula. Well, now into Pythagoras' theory. A squared plus b squared equals c squared. Well, in this case, we're going to use a squared plus y squared equals h squared. So replacing a gives us sine squared t plus replacing y with the parametric 1 minus cosine t squared will give us h squared. And I'm going to use the trigonometric identity real quick here because I kind of like all my sines and cosines in a row. So sine squared t is also equal to 1 minus cosine squared t. So that's what I've gone ahead and done. And we're going to take that formula and we're going to move it up. And I'm going to concentrate right now on expanding our b, or 1 minus cosine t squared. Okay. At the end of the day, when you do all your FOIL, first inside, outside, last stuff, you wind up with cosine squared t minus 2 cosine t plus 1. Now I'm going to move that down and over. I'm going to bring down my 1 minus cosine squared t. And now I have 1 minus cosine squared t plus cosine squared t minus 2 cosine t plus 1. Interesting. Wow. Well, we'll bring that formula up and we can go ahead and combine terms. So the negative cosine squared and the positive cosine squared go away, leaving us with 1 minus 2 cosine t plus 1. Now we have our expanded y value complete. That's 2 minus 2 cosine t. We're going to bring that formula back into the h value. Okay, so now we have 2 minus 2 cosine t equaling h squared. So what does h squared equal from our previous example? Well, that was the square of the square root of 2 minus 2 cosine, the quantity pi minus 2a. And of course, squaring a square root now leaves us with this beautiful derivation. 2 minus 2 cosine t equals 2 minus 2 cosine pi minus 2a. Ooh, let's take a look at that for a minute. You'll notice something very interesting. I have 2 minus 2 cosine on both sides. That equals 1. So we can just go ahead and remove that. And we're left with t all by itself equaling pi minus 2 alpha. Look at that beautiful formula. It's gorgeous. Well, let's go ahead and solve for a in case you need to look for the angle if you're given t. So we're going to go ahead and remove parentheses. We're going to swap sides. I like my variable I'm solving on the left, personal preference. We're going to go ahead and subtract pi and then divide by negative 2. And I'm going to clear the negative 2 out of the denominator. And we're going to just call it pi minus t over 2. And that's kind of neat too, but I think there's one more thing we can do to make it a little more tidy still. I like the idea of alpha equaling 1/2 the quantity of pi minus t. I think it's pretty. I think it just looks good, right? Now I give you both. You can find the time, or the t, or the theta. Sometimes they use that if you want the whole angle there. You can find t by taking pi and simply subtracting 2 alpha. Okay, and we know where alpha is. And if you want alpha, and you have the time, you can also find the tangent angle of that. That's the end of the presentation. Let's take a final look at all the little lines and fun stuff here. This is really just one of the most beautiful shapes on the planet for me. And let's go ahead and finish this out by taking a look at the sun-setting cycloid. Adieu. Okay, we're back. Hey, you know what? Wasn't that cool? Simple! Okay, what I want you to do is compare that final formula with the one I showed you at the beginning of the video. And I want you to use trigonometric identities to get from the law of sines problem to the law of cosine solution that I wound up with. Alrighty, that'll be a lot of fun. So go ahead and leave it in the comment section. As always, Prof. Hughes saying, class dismissed.